Hello, this is um, the next podcast, or you could call it the first podcast that's really about the core material of the course. And this is the group that are called GNC for Guidance and Control, which really you could call guidance, navigation, and control, because usually when you're worrying, the same people who worry about where you're pointing are worrying about where you are. So those two things typically go together. So either way. This is a fairly long, but actually not as complicated as it. I mean, this is a pretty complicated subject in a way. So either you get into all the mathematics of feedback control and all that, or you don't, which is why 137 is listed as a pre or co-requisite for the course. In this overview, I'm not doing that. What we're doing is getting to the point where you kind of know what the choices are and where each of those choices is applicable. And where you're going to get into numbers is in the actual design of the one that you're working on for your project or for the Sputnik. So we're going to talk about guidance and control. I'm on the first slide, this green slide, with a picture of one of my company's ancient projects. Putting there's a little aluminum box on the bottom, which is the actual satellite, and then the part with the solar panels on top was the customer's payload. And because we were so little, the payload was big, and so they had the assignment to put the solar panels because they had all the surface area. This picture was made down at NASA Marshall in Huntsville, and those two guys were our managers for that program. Okay, going on to slide 2. This is just sort of an overview, and in purple are pretty much all the topics, all the core topics that I try to cover in the class. The big decision for me is always which order to go in, depending on what I think is more immediately useful to you in doing your project. And the two that I lined up right away are the attitude control and the radio. Almost everything after that we could do later, and I'll probably shuffle them a little bit as I talk to you. But I do think that the power and mechanisms is definitely going to be important, since we're probably going to have some opening mechanisms for stability and control. And the power, even though we don't have solar panels, we do have a power budget and managing that. And probably go from there to the thermal, because it's something everybody worries about. The unfortunate thing about this class is you really need to know everything to get started on the system design. And so it's, it would be nice to do this class theoretically and then do the project, but that's the way it is. So I can only, plow through and give you the books, and you can always, scan through the other parts that you need to know right away. Slide 3, I'm taking a little detour before we get started to talk about design reviews, because in theory we have one coming up. And I think you've seen this slide before, but I just thought I'd throw it in there. The elements of the CDR, I think we threw this in before. If not, not that I'm saying that all of this has to be done in a tremendous level of detail, but it's a checklist, and you can go through the checklist and sort of, see what you can say about all these different topics. It's really handy to have I should say something about this, I should say something about that. The ones that are maybe a little bit unusual, when I say notions, at this point you may not know exactly how you're going to do the attitude control system, the power. All the systems are going to be notional in the sense that we think we're going to do it this way, and it's perfectly okay to say, here's my plan B. We have these two different competing ideas we haven't decided yet. At this phase, that's the right thing to do. A business case is probably not, particularly applicable, but who cares if we do this or not? Is there, the cliche is stakeholders. Who are the stakeholders in this? So, you can always say something about who cares about this, who's sponsoring it, what are they trying to get out of it, what are we trying to get out of it. That's a business case in a very general sense. And the critical technologies is put in there because in a real review, people want to know that. The risk areas, and then what's your risk mitigation plan? It usually comes up right in the CODR, the Conceptual Design Review, because it's sort of like, what are the things that you had to put in this that really don't exist yet, that you're hoping are going to work out to make this mission possible. So it's a little bit of aspirational design there. We want to call that out. I mean, a lot of times you do have something that has never flown before, and that's the whole point of the mission. So this is the opportunity to say, we've never done this before, nobody's ever done this before, and the point of this mission is to fly this, and here's how we're handling it in a way that, regardless of how it performs, the mission is going to survive. Then the program plan, and we've talked about a lot in the budgets, and then the suppliers. I mean, to the extent that you know it, it's very handy to say, here's where we're getting this, here's where we're getting that, and these are the critical things we need to get ordered right away because we think that the lead times are going to be very long. And then the last category, focus on something. The CODR by its nature is pretty top level, and you don't have that much detail yet to talk about, but usually you do have some things that you're really thinking hard about. And so if you do have something like that you're really thinking hard about and you have more detail on it, say, let me give you a quick look into this one particular system that we've already made some progress on. So those are the elements of the CODR. Then the next slide, which I have on the PDF, I'm reading off the same PDF that you have in Canvas, are homework questions. I'm not assigning these. They're kind of at the end. I'm previewing them. And as you can see, it says for a or your selected mission. I tried to write this as generally as possible to make it, applicable to multiple years. So obviously, if all the class is working on Sputnik, then, you're going to immediately zero this in on Sputnik, and that's fine. But the idea, like with the attitude control, pick two approaches. Maybe you already feel like, hey, I've got an approach. But from the point of view of the class, it's useful to say, look, if the aerodynamic thing didn't work because we're too high up and there's not enough drag and whatever, here's another idea that I thought of. Maybe it's magnetic or maybe it's something else. So it just kind of to force you to look through the list of possibilities and, pick them out. And then there's a second page of homework, which is a little bit, the language of Matteo to, these are the modes. What us old guy call modes, we now call use cases. And so, when you first get released from the, launcher, you're not going to have the aerodynamic shield, the aerodynamic drag device deployed. So that's a mode. And so usually satellites go through multiple modes, even in the attitude control, because then you go through a mode where you've deployed it, but you're not really stable yet. And how do you know that? And how do you know if you are getting stable? And how are you damping out any oscillations around the set point of your controller, in this case the controller trying to point you straight ahead. Normally with aerodynamic systems, they are their own damper. The aerodynamics provides you the damper, but that's not usually true. If you have a magnet, there's no damping. It's just going to try to point along the Earth's magnetic field, which is constantly moving, so the satellite is constantly moving, and every time it moves, it has an angular momentum, and it goes right through the 0 point, and it's just what I call first-order controller, constantly. So it's just a spring with no damper going back and forth around the 0 point. And the question is, how do we damp that oscillation? Okay, in slide 8, just some references on where you're going to find, attitude, determination, and control. I kind of purposely threw in all these different acronyms. That attitude, determination, and control, attitude control system, guidance and control, guidance, navigation, and control. Nobody has ever standardized on one of them, and everybody feels that they're talking about a different one. So I just threw all the different ones in here. The most general being, maybe this one, the attitude, determination, and control system. But then it leaves out navigation. So whatever. The SMAD book, there's a specific chapter, and in my book there's 2 particular chapters. Then I listed a couple of chapters on orbits, which are probably not super applicable to this mission, but anyway, I threw them in there. Then on the right, vertically, I notice that I yawn when I'm doing podcasts because I'm talking and not breathing. It's easier with music because there are pauses and you can specifically breathe, but in podcasts, you never breathe. Let me go to the next slide because I've got the link horizontally, which is a little more convenient for your eyes. I just happened to randomly find this video on YouTube, and it's a very, it's not, it's like these podcasts. It's not quantitative, but it's technical, and it really goes into some detail describing the problem of stabilizing Hubble and how it's done and the disturbances, and it's like a case study for this series of podcasts on attitude control. So I highly recommend it, and I think, I don't know, if I threw in a homework assignment on it or something else, I'll probably do that. Not because, just because it's such a nice video that it would really be a shame to not see it. And as you can see on the little, this is a screenshot off of the video, it's not super long. And, there's not much in the way of graphics. There's this level of graphics. A lot of times you're just looking at the narrator talking about it. She's a pretty sharp person, and she does a really good job of explaining it without getting into details, and yet very accurately. So it's rare to find a video that's that good. So, I highly recommend this one. Okay, so, being a cyclist and everything, and an early adopter of digital cameras, and I got the idea to take a digital camera with me on a race. So I took this picture, what my friends called my handlebar cam, but I was really holding it in my hand. It was a little dangerous doing that. But the reason I took the picture is that attitude control, one of my hang-ups about this class is that the students will think of it as, interesting, but not particularly relevant. And to me, space engineering is kind of, like I've said before, it's relevant to everything. And just, in many cases, the hardest possible example. When you're riding a bicycle, you're totally out of attitude control. You're totally thinking about attitude. We don't think about it that much because our cars are on four wheels. But when you're riding a motorcycle or a bicycle, you're definitely thinking about it. And whether you're going in a straight line and you want to keep the thing going in a straight line, or whether you're going on a curve and you want to make a curve of a constant radius, you have a specified thing, a specified trajectory, let's say, that you're trying to project the attitude through, which would be, like, we'd call that a maneuver. And the problems are not that different. And in fact, I sometimes use driving a car as an example of the different types of controller behavior and all that sort of thing. And as I think I mentioned in class, one of my friends from when I did my master's at Stanford in guidance and control, his first job after Stanford was he went to Japan and worked for Lexus, which was just getting started on their luxury line of cars and the whole idea of having a luxury line of Toyota. And they specifically were trying to upgrade the suspension and go to semi-active suspension. So the job of the semi-active suspension is to hold the car horizontal when you're going in a straight line and not go up and down, in the sense of air pockets, kind of, when you're going over bumps in the road. And so the car would look forward, try to anticipate the changes in the altitude of the pavement, and, control the body of the car so that it didn't dip and rise with every little perturbation. Of course, that's easier to say than it is to do, because maybe the dip is permanent. You can't hold it up forever. So it's actually a fairly hard problem. And I really don't know if the cars ended up using it or not using it, but they put a lot of time into studying it. Okay, so this is my kind of it's relevant slide. Being kind of the guy who is allergic to anything complicated, and having been a pilot before I went into, this whole space business, my first model of how you would point a satellite was how you point an airplane, which is you have three axes, roll, pitch, and yaw, and you have three control surfaces. For the pitch, you have what they call the elevator, the horizontal stabilizer in the back of the plane, which is a wing, that you can make the back of the wing tilt up or tilt down. If it tilts up, it pushes the tail down, and that pushes the nose up, and vice versa. Then you have the ailerons, which are on the wings, and they move differentially. If the left one goes up and the right one goes down, both of those forces cause the left wing to go down and the right wing to have more lift and go up, and then you can vice versa that. And then for the yaw, you have the rudder, which is also in the back of the plane. Looks a lot like the vertical the elevator, except it's left and right, like the rudder of a boat. So you move that vane to the left, and it causes the nose of the airplane to veer to the left. Because when you push that vane to the left, it creates an aerodynamic force pushing the tail to the right, and that tail going to the right looks from the cockpit like the airplane is. So it's super simple. It's Cartesian. It's fantastic. and I started to take guidance and control classes, and they're talking about spinning aircraft, spacecraft, and all these things. I'm thinking, why does this have to be so complicated? We solved this problem 100 years ago in airplanes very effectively. To convince myself that I had to complicate my life, I calculated how, thought about how could you do this on a spacecraft, what we do every day in airplanes. The trouble is we don't have air. So how do you make those forces on the three axes, the pitch, roll, and yaw forces? You would have to have thrusters, those arrows that are going up and down. Because if you want to have the aileron can go up or the aileron can go down. The rudder can go left or the rudder can go right. So you want to have an actuation in both directions, which means you need either two rocket engines or one rocket chamber that makes hot effluent, and then two nozzles and a valve that determines between the two, which seems like a more efficient idea, but generally isn't, because a valve that can operate at the temperature of hot exhaust gases from a combustion chamber is not going to be cheap, light, reliable, or easy to make, and therefore, it could be a lot of trouble for you. So generally, except in the case of cold gas thrusters, we have one thruster for each axis. So you end up with 6 faces, 12 thrusters. So then I kind of figured out, this gets into a little bit of calculation, what would be a typical disturbance torque in millinewton meters, very small amount, and I traded them in, I translated them into pound inches, 0.1 pound inch. It's not a very big disturbance torque. In the space world, it would be pretty sizable disturbance torque, but just to get an idea, and to make a long story short, calculated how much rocket propellant would it take to overcome that disturbance torque on 3 axes. And this is regardless of the size of the satellite. If the satellite's bigger, it's going to be more likely to have a large disturbance torque because, let's say, aerodynamic forces are going to go proportionally to the size. Gravity gradient forces are going to go proportional to the length. So, obviously as the satellite gets bigger, the torques on it are going to get bigger, or maybe not, obviously. But this is just kind of to get a rough order of magnitude type idea. And I came up with a number like 150 kilograms a year. So then I said, well, if we wanted to do that with cold gas, with nitrogen, compressed nitrogen, you'd need 3,000 liters of nitrogen stored on the airplane, or 800 gallons, if you want to call it, really get... I happen to have in my old house a 1,200 gallon water tank. And I can tell you it's pretty big. So, and this would be a pressure tank to hold, the nitrogen under pressure, stored at 2,500 psi. 150 kilograms of hydrazine, which is, the leading kind of simple propellant that's used in attitude control, would still be 150 liters, which is 150 kilograms roughly. So, it would be pretty ridiculous to do it this way because rockets are in general pretty ridiculous. In my book, I have an example. Why don't we use rockets to drive cars around? Luckily, we have the Earth to push against, to go forward and to stop going forward, to push the car forward or backwards and then to stop it from going backwards. We have this infinite sink of momentum in the Earth. If you don't have that infinite sink of momentum, your only choice, unfortunately, is to throw stuff out the back, kind of like a giant slingshot, to push yourself forward. And, whether that's efficient from a thermodynamic point of view, it's not particularly efficient from a mass point of view, because you have to throw a significant fraction of the mass, of your own mass, out the back in order to, do that. So you could say, well, airplanes do that. They, if you're at a high enough Reynolds number, if you're at a low enough Reynolds number, you're basically a screw, and you're screwing yourself through the air, through the water, right? Like a leaf like a seed falling from an oak tree, or the way very small animals of 1,000 cells or 10,000 cells, or even a water spider, how they move through the water, by pushing on the water as if it were a solid. But when we're in an airplane, we don't push on the air so much as if it would be a solid to make propulsion. We throw the air backwards. We use its momentum. The good news is that there's lots of air out there, so we just take the air out of the air and use that as our propellant and throw it out the back. Whereas in space, you don't have any air around you that you can scoop up and throw it out the back, so you need to carry it with you, and that becomes really obtuse. And in my book, I do that example for like a Mustang. How much stuff would we need to, given that you're always throwing it away and not taking advantage of the Earth to push against? So you might think, well, there are interstellar rockets, right? And they scoop up the interstellar material, hydrogen nuclei and, dust and stuff like that, and then accelerate it, some like electrostatically or something like that, and then throw it out the back much faster than it came in the front. So yes, you can get propulsion out of that. The dichotomy of that is there's not much of it out there. So you've got to be going already super fast, maybe even relativistically fast, in order to get enough of it, to accelerate you. So then if you're going relativistically fast, you can't accelerate it that much. So it's a great idea if it worked, but it doesn't. So it works a lot in science fiction, but it hasn't, turned out to be terribly practical, as a way of actually propelling things. Okay, so I'm going to kind of skip over problem 2 because it's a problem that we had a lot more, when I was in attitude control school in the 70s, which is a super long time ago. So we really can do pretty well now on DC. I mean, it is true that when you have a DC, meaning that things are not moving, it's harder to get a calibration point. And in the old days, we used to spin things so that we could mark the time when it passed the horizon and then the time when it exited the horizon and get a dwell time. How long did the sensor pointing at the Earth, and then how long was it pointing at space? I mean, with image processing, we're pretty good at, getting a 2D matrix of what the situation is around us. And but in general, for other reasons, spinning is usually easier than not spinning, unless you have a special case like we do. Okay, the next slide, which is number 13, even though there's no number on it, a feedback controller. Okay, you can see how old this slide is from the start here. I've never bothered in all these years to take it off. It's sort of like, to me, a marker of when I made the slide. Well, guidance and control, this part of it hasn't changed since there was the field. And I think you all know this, but I'm going to plow through it for a few minutes because it's the general field of how you control anything. And that typical example you read in textbooks is the temperature in your living room, right? And your living room has a thermostat, the thing that's supposed to make static the temperature. Therefore, it's a thermostat. And so you set the thermostat at 22 Celsius. My particular one seems to run in Celsius. So my GNC, thesis advisor had a Go Metric bumper sticker on his car way back then. And, he insisted to me that if I spent my whole life working in metric, it would become, and, it kind of happens after a while. I've gotten used to some things I still have to convert, but most things, go for me. So you set your thermostat at 22. And then the thermostat has in it a thermometer, a meter of thermo, right? A temperature measurement. So there's that sensor, the thermometer, and that goes into a little piece of logic that compares the set point with the reality. The guy said he wanted 22, and the room is actually on 20. So I have an error of -2. Then there's some sort of control algorithm that says, well, if you have an error of -2, turn the heat on, right? Start making hot water and pumping it through the radiators. So, that would be your control algorithm. And the one that I have in my house says that if the temperature is within 0.3 Celsius of the set point, you're golden, don't do anything. So when it reaches that, because otherwise, let's say it had a super accurate thermometer, the temperature would always be fluctuating. It would be 22.0001, and then it would be 21.9999. And the thing would keep cycling on and off the boiler and destroy it. So usually you have this, this null zone where you're not going to do anything, so that you're not constantly banging the system. I mean, in the worst case, you'd have an air conditioner and a heater. And you'd say, well, when it's too hot, turn the air conditioner on. When it's too cold, turn the heater on. And then if you had enough accuracy in your sensor, or enough noise in your sensor, even worse, you'd constantly be seeing, oh no, it's too warm, oh no, it's too cold. And you would be banging, what they call banging the controller, constantly saying, no, I need air conditioning, so that algorithm is super important, because otherwise you ruin everything. So in the algorithm, you think it's fairly simple-minded. Well, if the glass is not full, keep the water running, right? You want to fill a glass. So in that case, the sensor is your eye. You're watching the level of the water, and the set point is how much you want to fill the glass to. You've got in your mind, I'm going to fill it to the brim, or I want to leave, half an inch so I don't spill it walking over to the desk, or to the table. And then your eye is looking at that and saying, well, I want it to be up near the top, but it isn't near the top. And what's your control algorithm? Your control algorithm, if it's way down at the bottom, I'm going to turn the water on fairly hard. As it gets up toward the set point, I'm going to back off on the water flow, because otherwise I know I'm going to overflow the glass and get, myself all wet. So we have an actual linear controller, some sort of a linear controller in our brain that says, as it gets closer, decrease the flux of water. So that once you become conscious of that, it's kind of fun to think about all the things that are controlled by all kinds of other things, right? And, we do that with the speed of our cars, and, with the attitude of our bicycles, and, with just about any dynamic system that we encounter during the day. And the first serious GNC book I had was by a guy named Ogata. It was kind of the Bible. And it opens with the filling the glass with water. And I was reading and I was thinking, that this guy is really taking it all too seriously, But it turned out to be a fantastic model for some pretty advanced control problems. The human brain is a very good controller. It's not a first-order controller. It takes into account very easily the velocity. You don't just watch where the water is. You're actually watching how fast is the glass filling up. So that's additional information that helps you smooth out the controller. Okay, so then you have an actuator. Once your algorithm has said, we need more heat in this room, right? There's got to be something that actually turns the heater on. That would be just a bang, bang. It's either on or it's off. But you could also have a heater that has high, medium, and low, like the little electric cube heaters that everybody uses in the wintertime to, completely, annul all the energy efficiency that people have tried to build into dormitories and stuff like that. So your control algorithm may say, it's not super cold in here. It's 21, and therefore I'm going to turn the heater on to low. And if the temperature in the room is 17 and it's just friggin' cold, think about your cars with climate controllers. When you get in the car and it's a summer day and it's 100 degrees in there, it blasts the air conditioning at you, usually way more than you really want. Then as the car gets toward the interior temperature you set, it backs. So there's a speed controller on the fan or whatever it is. And then, okay, so that's what most people think of as the controller, right? The set, what you have in your thermostat. You have a set point, a thermometer, a way to tell. I apologize for the noise. I don't know, in the wintertime here in Rome, they're always, trimming the trees, and it's been going on for days. All my windows are closed, but it's, there's no way around it. So, got all the chainsaw guys outside. Then you have the control algorithm, and then you have the actuator, usually inside the thermostat, that closes a circuit that causes the boiler to go on. Then you have the other part that's not the controller, it's the control E, which in the case of your living room is the air in your living room, let's say, because it's usually the thermostat is measuring the air temperature. In my case, the thermostat is actually measuring the wall temperature, which is actually a little more stable. It's not a bad idea. Every time you open the door, it doesn't cool off the thermostat and then the heat goes on just because there was a cold breeze for a minute. So, but whatever it is, let's just call it your living room, right? The thing that you're trying to keep at 22 Celsius. So that, the actuator, the thing that's telling the heater to go on, and the heater itself has the net effect of heating up your living room. And unfortunately, were it so simple, that would be, your nice closed loop. You'd get the living room to 22, and the whole system would say, the sensor would say I'm at 22, the error thing would say I'm at 0 error, and the control algorithm would say, okay, do nothing, because we're where we want to be now. The trouble is that there are disturbances. People do open the door, the sun does shine in the windows. People open windows because they want to smoke, or whatever that is, or because when guests come in and you're all wearing your masks, it's normal to open all the windows so that you have fresh air coming in. So, it gets significantly colder in the wintertime. So those are disturbances. That's the outside world messing with your controller, right? And that causes, even though you got to 22 and you're totally happy, you may not stay at 22 because of the disturbances. So then the sensor is constantly watching for that. In the afternoon in the summertime and the temperature is already 23, and it might be smart enough to say, and it got there really fast, and so I think it's going to be at 24 in no time at all. So we should really go for it with gusto, with the air conditioner. So on a satellite, of course, it's usually not a thermometer. It can be a sun sensor. You want to be pointing it at the sun. It can be some sort of thing that tells you, am I at my attitude or not? So that is that's your generic control loop. And I'm tempted to say, well, what about passive control? The control algorithm doesn't really exist in that you wrote it. The control algorithm exists in the sense that if your arrow is not pointing in the direction that the arrow is going, there's going to be an actuator, which are the feathers on the back of the arrow, which develop a torque on the arrow, which causes it to restore to the original desire, which was that the arrow point in the direction it's going. I mean, that's a super good idea if you're trying to kill an animal. You really want the point of the arrow to be the first thing that hits the animal, not the side of the arrow. So, it's very practical minded to put the feathers on the back of the arrow, or to put them on the arrow at all. Okay, so it's pretty generic stuff. Most engineers have, seen this a long time ago, but not everybody in the world thinks this way. So I think it's worth the 5 minutes to go through it. A couple more slides and we'll quit to stay under 40 minutes. I threw this in, again, because of my desire to make the class relevant. But, obviously, in an office, you have the heating, ventilation, and air conditioning system with a thermometer. In an aircraft, you have two different kinds of things that you're controlling. One of them is the attitude of the airplane. Normally, you want it to be horizontal and not pointing up and down, right? So that's the kind of attitude of the airplane. But then you also want to control the flight path. You're trying to go from A to B in a straight line. And if you start to vary to the east or west or to the north or south from your desired line, you have to, which the wind may have blown you off, right? Let's say you're flying the airplane by hand and you're pointing at, an airport, Providence Airport, highly visible from a long way away because it's right on the Narragansett Bay. So you see the land, you see the Narragansett Bay, and then you see this big flat stretch of pavement out there, and that's the Providence Airport. Though there actually happens to be a second airport called Quonset Naval Air Station, and many, many times both professional pilots and students have accidentally landed there in the old days when it was an active airport. It looks very much like Providence, but anyway, if you get blown off course because there's a strong wind off of the ocean to the south, all of a sudden you're going to find that you're no longer pointing at the Providence Airport, you're pointing at Providence. And you're going to think, shoot, I got blown off course because I'm still pointing in the same compass direction, but I'm no longer pointing at the Providence airport. So then you have to do a fairly complex calculation. You could just point yourself back at the Providence airport, but you're going to get blown off again. So your controller actually says, hey, there must be a wind out there from the south, and therefore I'm going to overpoint. I'm going to point to the south of Providence Airport. Either you're going to calculate how much air, which is hard to do, or you're going to say, okay, 10 degrees to the south of Providence Airport. And then I'm going to see, does that hold? You know, we call that tack, your tack angle, the difference between the direction you'd like to go and the direction you're pointing in order to compensate for the wind. So, you know, aircraft are a fantastic learning situation for, you know, for this type of problem. So, and of course you have the altitude. The altitude of the airplane is like the speed of a car. You want to get there and then you want to stay there. You know, it's pretty, you know, it's a pretty straightforward controller. And the way you get there is you add more power to the engine. So that's your actuator, the throttle and the engine. And your sensor is the altimeter. Okay, we're there. So then you back the engine off so you don't have excess thrust anymore, so you're not climbing. You have just enough thrust to equal the drag, and your altitude remains constant. Okay, so, you know, the cup filling with water. You know, you have a grass cutting robot. You would like it to not cut, you know, the neighbor's grass or your feet off, or, you know, your bushes, you know, your sod. You really only, I mean, your, what do they call that stuff that they put on the ground to make weeds not grow? Anyway, you know, various things that are not grass. You want it to cut grass only. And your actuator is the wheels, which can be pivoted to make the thing go left and right, and you can also stop it. And one of the easiest ways to do that is to put a wire in the ground and tell the grass cutter, don't cross this wire, you know. So, okay, you know, various, you know, car speed and, okay. So let's, you know, there's a million of these, right? So I'll go on now to slide number 16, Anarchy Happens. This was Sputnik, and you can see the little picture of Sputnik. And I'm the guy who questions everything. Do we need all the assumptions, do we need solar panels? Do we need an attitude control system? Is it that important that we point in a particular direction? And, you know, the Russians are great at this. And I spent a certain amount of time working with the Russians. And I was doing assessments for the Air Force and for private companies about purchasing various aerospace things from the Russians. And anybody who's worked there and worked with them, you know, there's that old joke about, you know, how NASA built the zero-G, you know, pen, and you can buy them in the NASA stores. And they use some sort of osmosis to bring the ink always up because you don't have gravity to bring the ink down to the ballpoint or to the tip. And, you know, there's quite a bit of technology in that pen. And then, of course, you're going into zero gravity. And how do you even get the ink to be at the side of, you know, it's like a rocket engine in a way. You've got a tank, but in zero gravity, there's no law that says that the liquid has to be covering the part of the tank where it exits the tank and goes to the motors, which we kind of take for granted on the ground. That we call that the bottom of the tank, but in space, there's no bottom. So what the Russians, you know, the joke, and I don't know if it's even true, but it probably is that the Russians just use a pencil, right? And okay, NASA would argue that a pencil has many problems in space, mainly that it has graphite, and that the graphite makes fine particles, and those fine particles under zero gravity travel through the air, and NASA's worried about the astronauts breathing those little particles in, and so they don't want to use graphite. I mean, but on the other hand, I think the Russians figure, you know, people have been smoking a long time and living in dusty environments, and just how much graphite comes off of a pencil anyway, and the hell with it. So, you know, there is a kind of a very basic, you know, and the fact of that is that when it comes to doing things quickly and reliably, there's nothing like simplifying. Simplifying is your number one weapon for reliability, and the Russians are really good at it. So anyway, you know, unstabilized. The only problem with unstabilized is where's the antenna pointing? Because even if you don't have a camera, even if you're not sensing anything, like taking pictures of stars or the moon, or, Hubble is the exact opposite case. It's one of the most finely pointed satellites that we have. If you're not doing any of that, you're communicating with the Earth, beep, beep. And you don't want the antenna to be on the side of the satellite that's blocked by the satellite. There's various solutions to that, but the Russians did two. One is use a frequency that's low enough so the antenna is big enough so that compared to the wavelength, the satellite is small. I mean, if you do that experiment in like high school physics with the wave tank, you know that if you put a small object in the way, the wave goes right around it. It doesn't create a perfect shadow. On the other hand, if the wavelength is very short, like light, and you put your finger in front of it, it makes a shadow behind it. So the Russians used a relatively low frequency radio. I think it was 60 or 70 kilohertz. So the wavelength was many meters, 5 meters or something like that. The satellite is much less than a meter, and so the satellite will not block the antenna. Notwithstanding that, they put 4 antennas on the satellite and just divided the signal among the 4, figuring any one of them. And that way, if one of them breaks or isn't working, you're going to hear it from the satellite. Of course, us, super sophisticated types who worry about, the powder from graphite are going to say, yeah, but if you have 4 antennas, they're going to create an interference pattern. But the Russians also knew that 4 elements, centimeters apart or tens of centimeters apart, will not create an interference pattern in a wavelength that's 5 meters. So they were really on the safe side here. Okay, so anyway, that's the only thing they did, and that saved them the whole attitude control problem. The advantage are obviously cheap, simple, reliable, because it doesn't exist. So the cost of the attitude control system is 0. And you can still determine the attitude. It's not that you can't determine the attitude. Determination is one thing, the sensor. That's easy. Controlling it is harder because then you need to have the summer. Where do I want to point is already a complicated question. Like you're pointing lost in space wherever, and you actually wanted to be pointing. I mean, if you have a telescope, you go up on the roof. It's totally stable. It's not moving. And so you want to point at, the North Star. You want to point at Saturn. That's what I always try to point at first thing when I get up, right? Where the hell is it, right? So just knowing what your error is already super complicated, let alone what do I do about it? What maneuvers, which thrusters do I want to actuate? What's the optimal way to swing the satellite from what it's pointing to pointing at Saturn without overshooting, and the whole, how many orders of controller do you have, and what are you pushing against? And every time I put a pulse into the rocket engine, how many, Newton meter seconds of torque? It's, you're doing a lot of calculating. And then, of course, you have to have those rocket engines or momentum wheels or whatever they are, and the tanks that feed the rocket engines, which have liquid propellant in them probably, and that liquid propellant is going to slosh around and screw around with your attitude. I mean, it's a big leap to go to a full-up attitude control system, and yet without one, you can at least know where it is. Then, like you guys, if you have a 360-degree or 102 pi steer radian camera, and maybe you have 2 of them, you don't care which way you're pointing, because between those 2 cameras, you're getting the full 4 pi steer radian anyway. Basta que it's enough that you're not spinning very fast. That was the thing in the ham radio world we worried about a lot. We worried about what if we get dropped off spinning really fast? Or what if there's some asymmetric torque on the satellite that causes it to spin? That's usually been kind of one of those things you wake up at 3 o'clock in the morning in a cold sweat about that never actually happens. But there are passive dampers, and we usually flew with passive dampers. In the case of Sputnik, it's like it was so low that the aerodynamics became its passive damper. Okay, I will admit that unstabilized satellites, there are not that many of them up there, but they're really a cool thing because it makes it possible to build a really simple satellite. Okay, so we've been 43 minutes. I'm going to take a break and then come back and talk about the exact case. If you go to slide number 19, passive aerodynamic, that's the one we're talking about. So this is probably a good time to stop because I want to spend a little bit of time on it in a relaxed way. Okay, so thanks for listening to the podcast, and I'll see you around the corner on the next podcast of the series on GNC talking about aerotorque.